So far, we've considered only one specific plane wave mode of the electromagnetic field. Of course, that does not itself describe most electromagnetic fields we could have. If, however, we consider sets of modes, we can describe any field. Classically, we can always decompose any electromagnetic wave into a superposition of modes that are themselves solutions of classical eigenproblems of waves in resonators or free space, or possibly in other specific structures such as waveguides. Just as in quantum mechanics, if we set up these kinds of classical problems correctly from a mathematical point of view, these sets of modes give us complete sets for describing the waves in these classical problems. The approach to quantizing a more general electromagnetic field is quite straightforward now. We presume we've solved for these classical modes for their specific situation of interest, such as a resonator or a waveguide or free space, and we've established a set of classical modes. Then we quantize each one of these modes using the approach we've just described for one specific mode. Now, in a simple generalization of our approach, we will be describing the total field in terms of the annihilation and creation operators for each of these modes. So, the start of our quantum mechanical problem is to presume we've solved the classical problem for our modes.
So therefore, we postulate a set of classical modes of our electromagnetic field. And each of those is going to have the following form. So, an electric field as a vector for mode lambda, a function of position in all three dimensions, r, some specific vector function here, and our p lambda of t, some time-varying function out the front, and a constant for this mode, d lambda, we're going to work out. And we have a minus sign here, just in the way we've chosen to define this. And similarly, for the magnetic field in the mode lambda, also a function of position r in all three dimensions, and of course time. And again, a specific mode function here that we will have worked out, v lambda of r for the magnetic field, a time-dependent factor out front, q lambda of t, that we're going to work out. And again, a constant d lambda we're going to work out later as well. And we have c in here, as before, just for convenience in our algebra. Now, note, of course, that the actual electric field in this mode, this classical mode, the magnetic field, and these two spatial functions that are essentially giving us the shape of our electromagnetic mode here, these are all vectors. D lambda is a constant. And the forms we used for our plane wave example before are just one particular version of these. We had before that Ez, the z component, was some spatial function here, with a time-varying p of t here and a constant d. This was our electric field component. And similarly, we had a magnetic field component that we'd written in this form. And these are basically in the same form as we have up here, just special cases of that. And these are exactly the same form if we had chosen u lambda of r was minus z hat, that's a vector here in the z direction, times sine kx. So then this formula would be the same as that one. And similarly, if we'd chosen v lambda of r to be y hat cos kx is a vector in the y direction, a unit vector, this would be exactly the same as what we end up with up here. So these forms here that we've just written down will satisfy Maxwell's equations, as we have to have for our electromagnetic field, and the wave equation in free space if we require these two conditions. This one comes from one Maxwell equation and this from the other Maxwell equation. And we will also have to have, as we derived before, that if these satisfy the wave equation and Maxwell's equation, a relation like this between P and Q and a relation like this between P and Q. So we're just generalizing the results we got before. We won't go through them in detail here, but if we went through the same kinds of tests to satisfy Maxwell's equations before, then we would get these conditions. So we presume the classical electromagnetic problem with its boundary conditions has been solved to give these modes. So for example, we might have had some resonator and we'd solved the classical electromagnetic problem to come up with modes like these that satisfied the boundary conditions for the resonator and of course satisfied Maxwell's equations. So we presume that we've classically solved this classical eigenfunction problem to get these classical electromagnetic modes of the system. We'll also presume that the spatial functions that we're writing here are normalized over the entire volume of our classical problem. And of course, we're going to presume they're all orthogonal. That should happen anyway, since they're eigenfunctions of a classical Hamiltonian, as it will turn out. They're certainly eigenfunctions of a classical problem. So, for two possibly different modes, with indices for these modes, lambda 1 and lambda 2 respectively, then we would find that these two functions for the different modes are orthogonal. That is, the result of this integral would be 0. On the other hand, if these were actually the same mode, the result of this integral would be 1. So this we would write as a Kronecker delta. Again, this is the result of our classical problem that we have apparently solved for some modes in, say, a resonator, and these would be the conditions we would come up with, also forcing these functions to be normalized here. Hence, the Kronecker delta corresponding to a 1 when these are the two indices of the same mode, lambda 1 equal to lambda 2. And similarly, for the magnetic field spatial function corresponding to a mode lambda 1 and another one corresponding to a mode lambda 2, these would similarly be orthogonal, giving 0 result for this integral if lambda 1 and lambda 2 are different, and giving 1 if lambda 1 and lambda 2 are the same. That would be the normalization that we're imposing on this classical function here. Now, let's consider a classical superposition of such modes. So we're going to write some superposition summing over all the modes of the classical field here, and similarly of the magnetic field. And for the moment, these can be different functions for every mode. They can be different magnitudes, different coefficients in here, if you like. The total energy of a field like that would just be, as before for a classical field here, a total energy that starts from the energy density in the electromagnetic field, which classically we can write in this form, and then integrating over the volume of the problem. So if we use these particular mode forms that we have here, we get this result. So in this result then, we see this part here is coming from the square of the electric field, so a series of sums of products of these different functions from our sum here. And this part here is coming from our magnetic field, a series of different products coming from this sum here. And of course in this we've also simplified a little. We've got rid of the mu here by using 1 over c squared is equal to epsilon naught mu naught. So we've been able to take the epsilon naught out the front. Now, we can use the orthonormality of all of these spatial functions u lambda, the spatial functions for the electric field in our mode lambda, and of the v lambda, the spatial functions for our magnetic field in our mode lambda, in this relation here to simplify it a great deal. That will eliminate all of the cross terms where lambda 1 and lambda 2 are different in both of these parts of our integral here. So all we will be left with will be the parts where lambda 1 and lambda 2 are the same. All the others disappear, and because of the normalization, all we're left with then is this summation over lambda of d squared lambda times p squared lambda plus q squared lambda. So we can write a sum of separate Hamiltonians, one for each mode, where those separate Hamiltonians are therefore just a half epsilon naught d lambda squared times p lambda squared plus q lambda squared. Just a sum of separate Hamiltonians. We're merely rewriting this expression here using this form as we see in this relation. In each of these separate Hamiltonians, one for each mode, if we now choose d lambda equal to the square root of omega lambda over epsilon naught, then we can write our Hamiltonians for each mode in this form. And now we could find that this Hamiltonian, h lambda for mode lambda, and p lambda and q lambda, now obey Hamilton's equations. Remember before that we'd also had conditions relating p lambda and q lambda and their derivatives that we could figure out, just as we'd figured them out before for our single mode example. So with this choice now, we'll be able to satisfy all of Hamilton's equations for each of these Hamiltonians for each mode with our h lambda, our p lambda, and our q lambda. And we could check that. So now we proceed for each mode to quantize it by postulating a momentum operator for each mode in this form, minus ih bar d by dq lambda for the operator p lambda. And hence, we would change our classical Hamiltonian into a quantum mechanical one. So simply substituting for the p lambda in here using this operator, we would end up with this Hamiltonian for the mode lambda. We would next rewrite this Hamiltonian in terms of creation and annihilation operators, just like we did before. We'll define dimensionless units, xc lambda equal to q lambda over the square root of h bar, and the creation and annihilation operators explicitly then would become, as we see here, just analogous to what we had before. And so the total Hamiltonian for the set of modes would then be the sum of each of these Hamiltonians for each mode. So a rather elegant way of writing the Hamiltonian of the entire electromagnetic field.
So now we have a Hamiltonian for the complete electromagnetic field and all of the creation and annihilation operators that we need. Note that we started by formally presuming we'd worked out the classical modes of our system, whatever that might be, such as free space, a resonator, or a waveguide. Using the fact that these modes are mathematically orthogonal to one another, the resulting classical Hamiltonian just becomes a sum of the Hamiltonians, or of the energies, of each mode separately. There is no interaction between the modes because of their orthogonality. That has meant that our construction of the quantum mechanical Hamiltonian is just a simple generalization of the previous example we constructed for one mode. We simply add up the quantum mechanical Hamiltonians for the different modes to get the Hamiltonian for the entire electromagnetic field for our problem of interest. Now that we have the Hamiltonian for the entire electromagnetic field, we can look at the eigenstates of the entire electromagnetic field. And that will be the subject of our next section.